So my today's topic is about again moments, but I have taken moments class on the previous 3 occasions. Moment was discussed in class 6 as a topic, as introduction, as introductory topic, and moment was discussed as tool to evaluate statistical parameters in for binomial and Poisson distribution. Moment today will also be used to study something new. Okay, so moment is so useful tool in the statistical analysis that the discussion of it has come to the forefront again and again. And moment is a kind of tool from which we can deduce the other measures of central tendency, like mean, median, mode, or other measures of dispersion like standard deviation, mean deviation. Everything can be derived from moment. Probably you are thinking that statistical applications are not being shown, and I have been teaching you more about pure statistical analysis and mathematics for the last couple of weeks. It's because since you can see in your syllabus that the applied statistics, that is the application of statistics, is there in module 5 and 6. So before we go to apply, if we go to analyze the statistical nature of the system, we have to be equipped with the tools. When soldiers go to the battlefield, before that they weaponize themselves. So these statistical tools are very essential for study of statistical analysis, or analysis of the statistical situation. And we have to know about the statistical tools first. Moment is one of the most important statistical tools. So I am actually making you learn about these statistical tools. I am weaponizing you. And therefore, you can say that the past couple of weeks I have been actually taking the classes which can be named as learning tool classes. So today also I'm going to show you something, some sort of statistical things on the basis of the definition of moment, and you will find it interesting also. So with this introduction, I'm going to start my today's class. And again, I'm actually representing the definition of moment about origin, and which let me recapitulate the definition once again. The definition says that rth moment about the origin of the random variable capital X is denoted by mu r prime, and if capital X is the discrete variable, then mu r prime is actually defined as expectation of x to the power r, and is defined explicitly as summation small x, summation over small x means summation over all possible discrete values of the elements small x to the power r multiplied by the probability mass function. And for continuous case, the summation has been replaced by integration, and we integrate the integrand small x raised to the power r multiplied by the probability density function over the entire real line. That means all possible values of the random variable capital X. So this is about moment about, this is the definition of moment about origin. What is moment about mean? The rth moment about mean is defined as expected value of the difference capital X and the mean mu, and raised to the power r, that is mu r, and it is defined as summation over all possible discrete values of small x, x minus mu raised to the power r multiplied by the probability mass function of the random variable. R takes values from 0, 1 to up to infinity, and mu r is represented by the integration of this form when capital X is continuous. And to distinguish between moment about origin and moment about mean, I have used two notations. One is moment about origin is denoted by mu r prime, and moment about mean is denoted by mu r. Okay. Now we can connect these two definitions. One is moment about mean and another is moment about origin in the following manner. So here is a theorem, a mathematical theorem which states that the moment about means can be expressed in terms of moment about origin. I am giving you some time to copy this particular theorem in your copy so that when I shall be discussing my today's examples, you can take reference from this particular theorem, because I am not going to scroll up further. Fluctuating the screen in front of your eyes will pain the eyes. Okay, so I'm giving you one minute to just quickly copy this particular essential theorem. But fortunately, the deduction of the theorem will not be there in the syllabus, is not there in the syllabus, and we shall not be discussing how to deduce this particular theorem. But for the sake of your knowledge, this theorem can be easily proved by the help of mathematical induction. Okay, so you can try the proof by yourself, but that will not be helpful for your current course, because in current course we only deal with the statistical tools and their applications. The deductions are not mandatory. Write this particular formula in your copy and you see that the rth moment about mean has been expressed about, all the mu's have been expressed about mu primes. On the left hand side we have mu r, on the right hand side you have mu r prime minus rc1 mu r minus 1 prime mu plus plus minus 1 to the power I rci mu r minus I prime mu to the power I plus plus minus 1 to the power r minus 1 into mu to the power r, where r takes values 1, 2, 3 up to infinity, and r will take value from 1. It will not take the value 0, because mu, if we take mu r equal to 0, we will get mu minus 1 prime, which doesn't have any meaning. So therefore, here in this particular result, r will take values from 1. And alternately positive and negative sign will come. So first we have the positive term, then we have the negative term, then we have positive, then negative, then positive, then negative, and so on. So this is the formula which we are going to use in my today's class to analyze something which is a very new topic and also very interesting. So I hope that you have already copied this particular theorem. So I'm going to scroll down. We have dealt with the normal curve, and we know that normal curves are bell-shaped curve. The normal curve is a symmetric curve, and if we talk about a normal variate capital X, normal curve is symmetric about x equal to mean, or the normal curve is symmetric about x equal to median, or normal curve is symmetric about x equal to mode, because you know that since normal curve is symmetric, mean, median, and mode coincide at a single point. Normal curve is a bell-shaped curve, and on the left hand side of x equal to mu, it contains half of the total area. On the right hand side, it contains half of the total area. If we talk about standard normal curve, then we say that this curve is symmetric about z equal to 0, because if we standardize this, then the origin shifts to 0, and we name the variable as z. That is also standard normal curve and normal curve, both are symmetric. But if the curves are not symmetric, then those curves are called asymmetric curve. During the last couple of months, in newspaper and news channels, probably we've seen that the statisticians discussed about the effects of COVID-19 on the countries, and they said that during the months of September and October, it will take the peak. It will reach its maximum frequency. And they showed you several times the normal curve. So that smooth curve, that means something is happening and it ultimately reaches to its maximum and then it falls down. Okay, so that is called the smoothness. That is the smooth curve. That is called the normal curve. Okay, so you have heard about it. You have seen its picture in the television. or in the radio or in the internet. Now you look at these two curves below, which I have drawn over here. These curves are not at all normal, because the right hand side tail of this curve is lesser than the size of the left hand side tail. And here also the left hand side tail of the curve is lesser than the right hand side tail. Both of these curves are non-normal curves, or we'll say that these are asymmetrical curves. And why they are asymmetrical? Because they lack the symmetry of normalness. Okay, so that's why they are asymmetrical curves. Okay, so these two curves have lack of symmetry, and this is called the skewness. This particular drawback of the curves are called the skewness of the curve. This also can happen in the COVID-19 situation. If you start from counting the if you start from counting from February, mid-February of this particular year, and if we take all the relevant data of the people affected of this country, probably you will get this kind of picture. Okay, that means during the months of March, April, May, June, July, August, and in September, the peak point. So this is the negatively skewed curve. And after October, you may get a decline in the COVID-19 cases in this manner. And by the mid of next year, when the vaccine will probably come, the curve may take the shape of that. So try to visualize this particular curve from our current situation of COVID-19. So this is called positively skewed curve, and this is called negatively skewed curve. Epidemics, then other natural calamities cannot be normal at all. Okay, some skewness must be present over there. Okay, what is the measure of this skewedness? That is the important question. How to measure, how to quantify this skewedness of the curve? How much the curve? Measure of skewness means how much the curve is skewed. What is the quantification of that? Negatively skewed curves are also known as left skewed curves. Positively skewed curves are also known as right skewed curves. Here we are going to discuss how to measure the skewness of the positively or negatively, whatever it is, how to measure the skewness of this curve. And for this, I'm going to take the help of moment. So the skewness or the lack of symmetry of any curve which is not normal can be calculated by the following formula. Alpha 3 is equal to mu 3 by sigma cube. Alpha 3 is equal to mu 3 by sigma cube, where mu 3 is the third moment. Mu 3 is the third moment about mean. Sigma is the standard deviation. And you know standard deviation is the square root of variance, positive square root of variance. Or variance can be treated as the square of the standard deviation. So if sigma is the standard deviation, sigma square can be defined, and you know it, that it is Vx, variance of x, which is defined as E of x square minus Ex whole square. Now by definition of the moment which I described above, Ex squared has the definition mu 2 prime, and Ex can be defined in two ways. You can write in place of Ex as, you can replace Ex by mu, or you can replace Ex by mu 1 prime. So I have written here mu 1 prime square. Below you will see that in some cases I have written in place of Ex I have written mu, sometimes I have written mu, and sometimes I have written mu 1 prime. That is not a print, that should not be treated as a printing mistake. I did it intentionally just to remind you again and again that mu 1 prime and mu, these two things are same. Their meaning is same. So we have this. And what about this third moment? How to calculate mu 3? How can I calculate it? Now I'm going to show that how to calculate mu 3 with the help of that above theorem. I shall take the help of this theorem, and I will put r equal to 3 over here on the left hand side. If we put r equal to 3, then mu 3 will come, and on the right hand side we shall substitute r equal to 3, and we'll calculate, and we'll find some formula out of this, which will be the special case of this particular theorem, and we'll take the help of. that formula to calculate the third moment. Okay. I have considered this particular problem. The problem has been chosen from John Foynt book, Mathematical Expectation Chapter, probably exercise 1 of Mathematical Expectation Chapter. I cannot recall right now, but here from there I have chosen this particular problem. Here in this particular problem, a probability distribution has been shown to you. The probability distribution is having this particular probability distribution is having a random variable with 6 discrete values, 1, 2, 3, 4, 5, 6, and their respective probabilities. I am supposed to draw the curve, and I'm supposed to find the skewness of this particular discrete distribution. To start with, I have formed a table. I have formed a chart below first, where I put all the values of the discrete random variables starting from 1 to up to 6, and their respective probabilities have also been tabulated. But I was a bit confused whether these probabilities are indeed probability mass function or not, and you always should be confused if you start calculating things. First of all, if someone says that it is probability distribution, always verify whether it is indeed the probability distribution or not. And one of the verification steps is to take the summation of these discrete values or take the integration over the range to see whether the total probability is 1 or not. If the total probability is 1, the variance is, if the total probability is 1, the distribution is indeed a probability mass function or a probability density function. Okay, we know very well. Okay. Now, once we make this particular chart, what we see, let us draw, because we are supposed to draw the curve of this. So I have drawn the curve below. I'm going to show you two separate curves over here. One curve is this one, which is on the right hand side. Another curve is that one. You are probably thinking that how did I draw this particular curve? By Paint, Microsoft Paint, by drawing? No, I have drawn this curve using the Excel. So using the Microsoft Excel, you can also draw the normal curve. I'm in one of the subsequent classes, I am going to show you the usage of Microsoft Excel in statistical calculations. I'm going to take a class on that, and you don't worry about it. Using the Excel, I can draw this bar diagrams, this normal curve, every statistical calculation can be solved. And since you are actually going to apply statistics and you are going to deal with a huge amount of data, so obviously normal calculations, manual calculations will not help. So you need to know the statistical you need to know about statistical software. In nowadays, most useful statistical software is R. I also sent you a link of that in the Google Classroom. But if you do not have R, Microsoft Excel can also help you in this regard. Using Microsoft Excel, you can do this kind of statistical calculations, and we are very fortunate to have Microsoft Excel. So I have drawn these two curves over here, but you carefully see the nature of the curves. On the right hand side, I have plotted the bar diagrams. You can also plot the histograms. Only difference will be the gaps will not be there in the histogram. They will stick to one another. But if I imagine a smooth hand curve touching the midpoints of these pillars, then you see that some kind of a normal curve shape is coming. Okay, this particular figure is continuous, this particular figure is discrete, but they have some kind of connection in between them. What do they mean? They mean if I keep on increasing the values over here to infinity, then this bars will stick to one another in such a manner that they will not be able to distinguish them separately, and as if they will be treated as a kind of continuity. They'll be treated as having some kind of continuity. Now, also you know that in binomial distribution, if n tends to infinity and probability of success is not that small, it's significant probability of success, then a binomial distribution tends to follow normal distribution. And if we keep on increasing the sample size, almost every distribution tends to follow normal distribution. It is the outcome of one of the outcomes of central limit theorem. So these two curves, by these curves we have seen that the problem which we are going to deal with today is actually normal curve. It's not positively skewed and it is not negatively skewed. I am going to measure the skewness of this normal curve using the above formula. So we know the formula is alpha 3 and it is defined as mu 3 by sigma cube. Now one by one I'm going to calculate the factors. Okay, so first of all I'm going to calculate mean, which is mu1 prime or mu, because if you are going to calculate third moment, the third moment is what is actually based on the mu primes, different kind of mu primes. One of the mu primes is mu1 prime. So mu1 prime is expectation of capital X. I have calculated it. I am not telling the details of that because several times it has been discussed how to calculate Ex. Then we have to calculate mu2 prime. So mu2 prime is similar to Ex square. I have calculated this. Then Vx, variance X, we need sigma square. So variance X is sigma square. I have calculated this. Okay. And lastly, mu3. I'm supposed to find the mu3. I have calculated Ex and Ex square just to calculate Vx. Mu3, in mu3 also mu is present. Okay, so mu is already calculated. Now if you put r equal to 3 in the formula, in the theorem, you will find this. So the special case will be this. So mu3 can be expressed in terms of moment about origin in the following manner. So mu3 becomes mu3 prime minus 3 mu2 prime mu plus 2 mu cube. So mu3 prime is this one. This is the formula where mu1 prime and mu are same. Mu3 prime by definition is calculated as expectation of capital X cube. Okay, capital X cube is what? Capital X cube is summation over all discrete values x cube into fx, which is 58.1. And once I calculate each and everything, we are going to substitute the values one by one into this particular formula, and we are calculating mu3 as 0. The value is coming out as 0. And lastly, we are going to substitute the value of mu3 and sigma in the formula of alpha 3. So mu3 is 0 and sigma 3 can be written as sigma square into sigma. But sigma square is 1.45, we have already calculated. Sigma will be under square root sign 1.45. So I have written over here, and alpha 3 has come out to be 0. Am I right? Answer is yes. Because in case of normal curve, the skewness is always 0. And if the curve is positively skewed, the skewness, the measure of the skewness, alpha 3, will be greater than 0. If the curve is negatively skewed, the skewness will be less than 0. So the skewness is coming out as 0 in the above calculation. It is the sign that we have done nothing wrong. The calculation is all right. For normal curve, the skewness must be 0. But if you change the question a little bit, suppose I am making these values in such a manner that the total probability is 1, but the curve is not normal. Okay, you can do this particular homework. You can choose the values arbitrarily. Just keep in mind that their total of this probability must be equal to 1. But if you do this kind of manipulation with the chart and it becomes a positively skewed or negatively skewed curve, that means your value, the result will not be 0. Your result will be either some positive, will be having some positive value, or will be having some negative value. And also you see that one thing I must say, that the word negative skew doesn't mean that the curve must lie on the negative quadrants. Negatively or positively, these words are based upon the left tail or right tail. If the left tail is longer, it's negatively skewed. If the right tail is longer, it is positively skewed. So never confuse yourself that negatively skewed means the some part of the curve will be on the negative quadrant. Okay. So I have measured the skewness of the normal curve, and the skewness of the normal curve has come out to be 0. You can choose any other examples of this sort, and you will find the same result over there. Our next discussion is about Cartosis. So what is Cartosis? Now you see I have pasted something. I have taken this particular image from Google and I have pasted over here. The picture clearly shows you that in this particular case there are all the curves which have been shown. One, the blue colored curve, and another is this brown colored curve, and this green colored curve. All these curves are normal curves. They are not positively or negatively skewed curves, but there are some sorts of difference among them. The blue colored curve is much peaked than other curves relative to the other curves. The brown colored curve is moderately peaked, and the green colored curve is less peaked relative to the other curves. So the most peaked, the curve which is most peaked is called leptokurtic curve. The curve which is moderately peaked is called normal curve, or sometimes it is called a mesokurtic curve, MESOKURTIC. Since this image has been chosen from Google, mesokurtic word was not mentioned over there, but I have mentioned this particular word below, mesokurtic. So this word will be mesokurtic. And if the curve is like that, or more like less peaked relative to the other curves, such a curve is called platykurtic curve. Here they have mentioned in the image, they have mentioned this as normal, but don't think that platykurtic curve is not normal or leptokurtic curve is not normal. Everything is normal. Normal means what? Normal means it should be of bell shaped, and it must be symmetric about the midpoint. Okay, and the left tail is equal to the right tail. That is normal. So every curve shown in this particular figure is normal actually. The correct representation of this brown shaped curve, brown colored curve should not be normal. All of these curves are normal, but the correct word should be here is mesokurtic. So the Cartosis is represented by, Cartosis measures how much the curve is peaked. Okay, how much the curve is peaked. Just like skewness calculate how much the curve is skewed, Cartosis measures how much the curve is peaked. Question is how to measure the Cartosis of the curve. How to identify whether a curve being normal is leptokurtic, platykurtic, or mesokurtic. The answer lies in the formula that we measure the Cartosis by using the formula alpha 4, which is given by the formula mu 4 by sigma to the power 4. Mu 4 is called the fourth moment about mean. So first of all, what I have done, I have put r equals to 4 in the theorem, and by substituting r equal to 4 in the theorem, I have expressed mu 4 in terms of mu 4 prime, mu 3 prime, mu 2 prime, and mu 1 prime, but mu 1 prime is same as mu, so all the mu 1 primes have been replaced by mu. And for the sake of your understanding, I have shown here that mu 4 prime can be expressed as expectation of capital X to the power 4. Mu 3 prime can be expressed as expectation of capital X cube. Mu 2 prime can be seen as expectation of x square. Mu can be seen as expectation of x. This part has been shown to you for the sake of your understanding. After calculating each of these sections, I have substituted the things over here, and alpha 4 came out to have the value 2.59. 2.59 is approximately equal to 3. Now I have used one of the concepts of numerical analysis here. Since 2.59 is approximately equal to 3, okay, so I have rounded it off. But if you think that the difference between the value 3 minus 2.59. How much? The difference is 0.41 difference. The 0.41 difference should be counted. Okay, why is it not exactly equal to 3? That means in every measurement, some kind of bias is always there. Some kind of error is associated with every measurement. And therefore, it is exactly not equal to 3. But since it is actually 2.5, we always, in numerical analysis, we always count the values greater than 2 or equal to 2.5 as 3. So I have rounded it off. And also for mesocartic curve or normal curve, actual normal curve, which we actually the moderately peaked curve, the value of alpha 4 must be equal to 3. So I have written here a note. You see, the note is, for normal curve or mesocartic curve, the value of the kurtosis will be exactly equal to 3. For leptocartic curve, if the curve was leptocartic, it has to be greater than 3. And if the curve is platycartic, it has to be less than 3. So this result has to be, this particular note have to be remembered. Okay, so whether the curve is platycartic, mesocartic or leptocartic, this analysis is just as important as the analysis of whether the curve is positively skewed, negatively skewed, or moderate or not skewed at all. Okay, while I did the calculation here, after calculating things like this, I have suddenly, yesterday I was doing the calculation, I found that the value of alpha 4 came out suddenly to be 1000.3 something like that. And I was scratching my head, why did it happen? Obviously I have done some kind of mistake. This kind of absurd result shouldn't come. Okay, so the mistake lies in the fact that whenever my suggestion to all of you, and that was also a kind of lesson to me in yesterday when I was doing the calculation by hand, that whenever we should do the statistical calculation, it will be always good, it will be always a good practice to make a chart like this. Always try to make a chart or table. Okay, and this table will never betray you. The probability, the chance of doing mistakes will be minimized. So here in this particular chart, I have shown the values of x as has been given in the problem, the value of fx as has been given in the problem, and I have calculated the terms like x into fx, x square into fx, x cube into fx, and x to the power 4 into fx. You know that the summation of this x fx will give you expectation of capital X. Summation of x square fx will give you the expectation of capital X square. Summation of x cube will give you, summation of x cube fx will give you expectation of capital X cube. Summation of x to the power 4 fx will give you expectation of capital X to the power 4. I have written all the summations and I have made them yellow colored. Okay, so my suggestion to you, always use the table to calculate things. Otherwise, the probability of doing mistakes or putting errors into your calculation will increase. Okay, and lastly, before I conclude my today's class, that I have shown 3 results over here. You can see what is the difference of these results from the earlier one. The difference is here in these results, on the left hand side, mu moment about the origin have been written, second moment about the origin, third moment about the origin, and fourth moment about the origin. The moment about the origin here has been expressed in terms of moment about the means. Only I have written here mu1 prime in all of these cases, because you know mu1 prime is same as mu, so that will not be a much of importance. Okay, but on the right hand side, other values of mu's are not having prime sign. Mu2 has been written. Mu2 is the second moment about mean. So the second moment about origin has been expressed as in terms of second moment about mean. Third moment about origin has been expressed in terms of third moment about mean and second moment about mean. Fourth moment about origin has been expressed in terms of fourth moment about mean, third moment about mean, and second moment about mean. The thing has been, the role has been reversed. But don't think that the earlier formula, that means when I wrote mu2 in terms of mu2 prime or mu3 in terms of mu3 prime, I only changed the side of the items from left to right, from right to left to get this. No, that hasn't been done in the manner. You can check it by yourself. By changing sides, these things will not come. Okay, the coefficients will not be similar. Okay, these things can be calculated in a different way, but that analysis will not go into the details because it is beyond the scope of our syllabus. Okay, these calculations, the proof of the theorem which I have shown you earlier in the beginning of this session, all these are actually taught in statistics honors course. But since we are actually here to learn the applicability of statistics in nature, then we shall only learn about the tools and how to use it. So in today's class, we have learned two important things. One is called the skewness. That means how the curve is skewed, how much the curve is skewed, or was it indeed skewed or not. If it is skewed, whether it is skewed to the right or skewed to the left, that has been measured with the help of moment. And also, we have measured how much the curve is peaked. All these kind of analyses are actually very important in statistics. How much the curve is peaked. Say for example, this is the limit. This is the maximum number of people died in Italy during the COVID-19 situation. That maximum number is much more higher. So the Italy's curve is leptokurtic. Suppose this is the case of, say, China. Okay, the maximum number of people died in China is different from maximum number of people died in Italy. And suppose this is the case of India. India has already obviously reached some maximum, but it is lesser than that of China and Italy. So this analysis of how much the curve is peaked is also very important. Okay, so try to think over these things. Yeah, just don't do the calculations mechanically. So I am going to conclude my today's class at this point. Tomorrow, day after tomorrow, we are going to meet again with something more about these topics. Okay, so till then, goodbye.